This video introduces the concept of bond order, which represents the net amount of bonding between two atoms. We can consider the molecular orbitals of the hydrogen molecules to be formed from the overlap of the 1s orbital of the hydrogen atoms. As each atomic orbital can have either a positive phase or a negative phase, there are two possible ways in which these atomic orbitals can overlap. Both orbitals can be in phase, have the same phase, or they can have different phase. They are out of phase. In-phase overlap is constructive and results in the formation of molecular orbitals with a large amplitude and consequently high electron density between the nuclei. Out-of-phase overlap is destructive and gives a molecular orbital with zero amplitude, therefore zero electron density between the nuclei. Constructive overlaps lead to bonding molecular orbitals, and we call these sigma orbitals. Destructive overlaps give rise to antibonding molecular orbitals, and we indicate these with a sigma star. This graph shows a so-called molecular orbital diagram, where the relative energies of atomic orbitals and molecular orbitals are shown. The rules for filling molecular orbitals are the same as those for filling atomic orbitals, meaning no more than 2 electrons can occupy an orbital. We have to fill the orbitals from the lower energy up, and we fill degenerate orbitals according to Hund's rule, meaning all electrons have to be unpaired to start with. In the case of the hydrogen molecule, the 2 electrons in the 2 atoms fill the bottom sigma bonding orbital. It's now a good time to introduce the idea of bond order. Bond order is defined as 1/2 of the number of bonding electrons minus the number of antibonding electrons. In the case of the hydrogen atom, as we have 2 electrons occupying the bottom sigma bonding molecular orbital, the bond order is 1/2 multiplied by 2 minus 0 orbital electrons in the antibonding orbital, therefore a bond order of 1. We call this a single bond. We can use molecular orbital theory to rationalize why 2 helium atoms do not combine to form a molecule of helium-2. The electron configuration of helium is 1s2. Therefore, the hypothetical molecule would have 4 electrons. 2 of these electrons would populate the bonding sigma 1s orbital, while the remaining 2 electrons would occupy the antibonding sigma star 1s orbital. The total electronic energy of the helium-2 molecule will therefore be exactly the same as that of 2 isolated helium atoms, as the destabilizing effect of the electrons in the antibonding orbital cancels out any stabilization due to the electrons in the bonding orbital. As there is no energetic advantage, a molecule is not formed. This is confirmed by the number bonding order, which we can calculate. 1/2 2 minus 2 gives 0. Let's look at the bond order of the cation helium-2 plus. Let's imagine that this cation is formed by the approach of 1 helium atom with 2 electrons to 1 helium plus cation with 1 electron. Their molecular orbitals will be formed and filled initially with 2 bonding sigma electrons and a single sigma star electron. So the bond order for this system is 1/2 multiply the number of bonding electrons, 2, minus the number of antibonding electrons, 1. So the bond order ends up being 1/2. Now, such bonds are actually quite common in chemistry. Helium-2 plus as a cation can be prepared by passing an electron discharge through a sample of helium gas. The cation is quite unstable but survives long enough to allow for its study. So a way to justify this is to say that the bond order of 1/2 is still better than a bond order of 0, and the overall energy of this molecular orbital is lower than the overall energy of the two isolated systems. Therefore, the molecule has a chance to form. Let's look at the beryllium-2 molecule. Beryllium has 2 electrons, of which 2 are buried too deeply next to the nucleus to take part in any molecular interaction. Therefore, the 2 valence electrons are the ones we'll be worrying about. Out of these 4 electrons, 2 go in sigma bonding orbitals, 2 go in sigma star antibonding orbitals. Therefore, the bonding order of the molecule beryllium-2 is 0. In sophisticated examples in the lab, beryllium-2 has been synthesized, but its bond dissociation energy is extremely low, meaning this molecule is very unstable. On the other hand, if we subtract 1 electron and form the cation beryllium plus, we get a bond order of 1/2, which makes for a much more stable molecule with a dissociation of 2 electron volts. Finally, if we look at molecular orbitals for larger molecules, the same rules apply. The only difference here is that we don't only have sigma and sigma star molecular orbitals from 1s or 2s atomic orbitals, but we also have sigma and pi orbitals formed from p orbitals on the atoms. Here's a sketch of the molecular orbitals from the p atomic orbitals. In the case of the nitrogen molecule N2, we have 10 valence electrons. As we fill the molecular orbitals, we see that we have 8, 2, 4, 6, 8 orbitals in bonding electrons in bonding orbitals, and only 2 electrons in antibonding orbitals. Therefore, the bond order for the nitrogen molecule is 3, meaning that the nitrogen molecule has a triple bond.